In this lecture, let us consider an example. Okay, so let us say our message signal is a pure sinusoidal signal of frequency FM. So m of t I can write as a suffix m times cosine of 2 pi suffix mt. This m indicates message signal amplitude. Now what is your modulated signal? X of t is equal to a times let's say, in order to differentiate the carrier amplitude and message signal amplitude, let me put a suffix c cos omega ct plus a suffix m cos omega mt multiplied by a suffix c cos of omega ct. Now rearrange this expression. AC can take outside commonly. 1 plus a suffix m divided by a suffix c cos of omega mt multiplied by cos omega ct. Now this is the modulated signal in the general form. Modulated signal with carrier. Okay, so that is AM signal with carrier. So if you want to avoid, or if you want the envelope of the signal to follow the message waveform, what should be the condition? This AM divided by AC must be less than 1, right? We defined in the previous lecture that E of t is equal to what? 1 plus m of t, but instead of m of t I have the amplitude. So AM by AC maximum value, it can take 1 for a cosine wave cos omega mt. Okay, so this guy must be less than 1. Now let us give a new name for this, that is modulation index. Therefore the above expression becomes x of t is equal to AC times 1 plus mu of cosine omega mt multiplied by cosine omega ct. Okay, so what should be the condition on mu? It should be less than 1 for envelope to follow m of t, otherwise distortion will come. Okay, so mu must be less than 1 for envelope. This already we discussed. Okay, n for envelope to follow m of t. The modulation index should be less than 1. So the percentage of modulation index should be less than 100%. So the message signal spectrum is as follows. You have cos omega ct, you take Fourier transform. Let me for the time being forget about the magnitude. It has two frequency, del of f plus fc plus del of f minus fc. That means you have two frequency component. One is sitting at fc and another guy is sitting at minus fc. Okay, it has impulses at fm and minus fm. This is your message signal m of f. After modulation, the spectrum of x of t is x of f. The spectrum looks like this. So you have the impulse function at fc, and then at fc plus fm you have one carrier component, and fc minus fm you have another message signal component. Sorry, this is carrier and this one is upper sideband and this guy is lower sideband. Similarly, in the negative frequency axis also, I will have this one carrier, and here I have lower sideband, and here I have upper sideband. This is minus Fc plus B, and this one is minus Fc minus B, and this is 0, and this is your frequency axis F. Okay, now these are the two sidebands, upper sideband and lower sideband. Fc plus Fm is the upper sideband, Fc minus Fm is the lower sideband. Similarly, on the negative frequency axis also, minus Fc minus B is the upper sideband, and minus Fc plus B is the lower sideband. Actually, these together, I mean this Fc plus Fm and Fc minus Fm and Fc plus Fm constitute the double sideband. Okay. Now, if you take this this one and this one constitutes the upper sideband, minus Fc minus Fm and Fc plus Fm. Similarly, minus Fc plus B, Fc, I am sorry, what did I do? This is wrong, this is not B, it is Fm. Okay, so minus Fc minus Fm, Fc minus Fm, these two guys constitutes lower sideband. Okay, so these two constitute upper sideband, and these two guys constitute lower sideband. That's it. Okay. Now, if you expand this expression, where is it? Yeah, this one. X of t equal to a times 1 plus mu cos omega mt plus cos omega ct, then you will get x of t is equal to a times cos a suffix c times cos omega ct plus a times mu times cos omega ct and cos omega mt. Now, again, if you rewrite AC cos of omega ct plus this one cos a cos b, so cos a plus b plus cos a minus b, so a suffix c times mu by 2 cos of omega c plus omega m times t plus a suffix c mu divided by 2 cos of omega c minus omega m multiplied by t. Now, how much power is carried by the carrier? By the way, where is the carrier? This is my carrier. Now, carrier power, we know the standard formula, that is AC square by 2. Okay, so this is my carrier power. What about this one, omega c plus omega m? This is the upper sideband. Okay, so what about the upper sideband power? The whole square by 2. So this becomes AC square mu square by 2 square becomes 4 whole divided by 2. So therefore, this upper sideband becomes 1 over 8 AC square mu square, and this guy contributes the power of same amount, AC squared mu squared by 8. What is the total power in the modulated signal? You add these two guys. So AC squared mu squared by 4 is the total power. The power in the two sidebands, okay, which is the useful power transmitted here. Okay, therefore the useful power transmitted as a fraction of the total transmitted power. Okay, total power transmitted. Therefore, how should we define the efficiency? The efficiency equal to useful power. How much? A squared AC squared mu squared by 8 divided by AC squared by 2. total power, right? So AC squared by 2 plus now this is 2, right? 4, because the useful power is 4 here. Okay, the numerator it is 4. The denominator AC squared by 2 plus mu squared A squared by 4 AC squared. This is both in the numerator and the denominator we have AC squared. You can pull out. If you rearrange this becomes mu squared divided by mu squared plus 2. So this is the power efficiency that you will have for the modulation index of mu. Now what is the best power efficiency that one can achieve? The best power efficiency you can have will be obtained when mu is 1, maximum value it can take is 1, right? If you substitute 1, then the maximum efficiency is 33.33% for mu is equal to 1. So this is the maximum efficiency that one can achieve for AM system with a sinusoidal signal as a message signal. If you want to plot this power efficiency in the form of picture as a function of mu, it looks like as follows. So let's say this is maximum 100%, okay, carrier power. Okay, when mu is equal to 0, that means what? If you look at the equation, when mu is equal to 0, there is no power in the side bands, only carrier power is generated. Therefore, when mu is equal to 0, your maximum will be 100% carrier power, and slowly it drops down when mu becomes 1. When mu is equal to 1, the carrier power itself 67%. Remaining 33% only occupied by the message signal. So carrier alone needs 2/3 of the power. 2/3 of the power. So 2/3 of the power will be spent on carrier. Okay, so this is the profile of the carrier power, and that comes down like this. And this is mu is equal to 1. This axis is mu. If mu equals 0, all the power are in the carrier. If mu equals 1, 67% of the power is in the carrier. So as far as power in the sideband is concerned, if mu equals 0, there is no power in the sideband. If you look at the expression, you will come to know. See, no, if mu equals 0, no power in the sideband, all are 0. If mu equals 1, then 33% of the power is there in the sideband. Suppose if you want to plot, let's say, mu versus sideband power. When mu is equal to 0, sideband power is 0. So you start from 0. And it linearly increases to maximum value of how much? 33%. When it reaches at what point? When mu equals 1. When mu equals 0, it is 1. Okay. So this discussion we have carried out is valid when the modulating signal was purely a sinusoidal signal. One can prove that for a more general kind of modulating wave, message wave, m of t, the power efficiency can be increased, but under no circumstances it will be more than 50%, like we discussed earlier in one of the lecture. So you cannot achieve more than 50%. Okay, so let us summarize. So far we have discussed two kinds of amplitude modulation, Dsbsc and Dsbam. Okay, this one is a normal name. Okay, when I say amplitude modulation, that means Dsbam with carrier. Amplitude modulation means it always talks about with carrier, but more precisely we would say DSB with carrier and DSB without carrier. So what are the pros and cons of this? Dsbsc is efficient in power. Bandwidth efficiency is same for both of them. Why? This guy also 2 times B and this guy also 2 times B. So there is no difference in bandwidth usage. Okay, so twice the message bandwidth as the final transmitted bandwidth. However, in terms of power efficiency, which one is better? Dsbsc is much better. Okay, we have said that some situations we will be ready to sacrifice power efficiency for an economical receiver point of view. So when you want to do that, like in broadcast applications, you can choose DSBAM with carrier. However, when power efficiency is important, like in point-to-point communications, you should go for Dsbsc. Okay, so power efficiency is very important in that. Okay, we should not use this Dsbsc in broadcast applications. You always go to DSBAM rather than Dsbsc. Okay, for broadcast applications, you always go for DsbAM. What is the other difference that you have seen? In this case, the envelope will be proportional to mod of m of t, and here the envelope is proportional to m of t itself. Okay, and one more thing is, we said that there is a disadvantage of Dsbsc, that is, if your local carrier is out of phase, then the incoming carrier out of phase with the incoming carrier, then you intend to lose the signal. Okay, so there are, let's say there are perfect frequency synchronization, but there is a loss of phase synchronization, then the output is proportional to m of t cos theta, and when theta becomes 90 degree, then you will completely lose the information. See, in the Dsbsc we said output y of t is equal to m of t times cos theta. When theta becomes pi by 2, then output becomes 0. Okay, so this is the disadvantage of Dsbsc modulation. Actually, we can convert this disadvantage into advantage. Now, you can ask a question, how can we convert this disadvantage into an advantage? Okay, what I will do is, I can put two signals on the same carrier, one using let's say two message signals m1 of t and m2 of t. m1 of t uses the bandwidth, uses the carrier cos omega ct, same carrier frequency, and the m2 of t uses sin omega ct. Okay, and then look at the receiver. I assure that there is a perfect phase synchronization for each of them. So I can separate out the two. That is the beauty of these two kind of things. So this is something called orthogonal signals. Okay, we will be studying about this in a later stage, about orthogonal signals. These two carriers are orthogonal carriers. So they have same carrier frequency, but if you want, you can separate out one guy from the other guy. That's what we mean by orthogonal. Okay, I can separate out the two without interfering from one from the other. So this is a very nice thing one can do, which is called something called quadrature carrier multiplexing. Quadrature carrier multiplexing. So that is, you can put two signals on the same carrier. So we do not think of putting two signals in the same carrier. Okay. So that we will discuss in the next lecture. So let me stop at this point. So in the next lecture, let us talk about quadrature carrier multiplexing. Thank you.